Hello everybody, welcome to another short tutorial on algebraic geometry. In this one we are going to continue talking about regular functions, and we're going to discuss an extension theorem for regular functions, which will remind some of you of a similar theorem in complex analysis, where you extend holomorphic functions to singularities. This is in the same spirit. So assume that you look at the punctured plane A2 without the origin, and consider the ring of regular functions on this punctured plane. Then what I claim is that this ring of regular functions is really the same as the ring of regular functions on all of A2, so the plane without leaving out the zero. Or in other words, we can extend the regular functions in a regular way to all of A2, and thus the similarity with the result in complex analysis. And well, I've already sketched the proof here. So first, note that this set, the punctured plane, is open because 0 is closed in the Zariski topology, and you can write this this set as a union of two distinguished open subsets. dx1, this is the non-vanishing set of the polynomial x1, and similarly for x2. And since these are both open sets, of course, their intersection is also open. And on this open set, the intersection of these two distinguished open subsets, we can look at regular functions. Now remember, a result about regular functions on distinguished open subsets was that you can write every regular function on a distinguished open subset in the form some polynomial, for instance, like this on D2, some polynomial G2 divided by some power of the polynomial which is non-vanishing on this distinguished open subset. So in this case, on dx2, you can write every regular function in this form. And on D1 you can write every regular function in this form. So suppose we have a regular function phi, which by what I've just said can be written on D1, dx1 in this form, and on dx2 in this form. Then we can, without loss of generality, assume that x1 doesn't divide G1, and this means that G1 x2 to the n minus G2 x1 to the m is 0. But let's look more generally at the set V of this. So this is the vanishing set of this polynomial. This is, of course, by definition of the Zariski topology, this is closed in the Zariski topology, and it contains this intersection. And now remember that the Zariski topology has the property that every open set is dense. So the closure of this intersection is contained in the vanishing set of this polynomial, and is all of A2, since this closure of this open set is all of the space. So what we get is that this equality here is true on all of A2. And now let's find out what m is. Suppose m is greater than 0, then we can look at this and conclude that x1 has to divide g1, but this is not possible because we excluded this possibility. So we have a contradiction which arises from the assumption that m is greater than 0, so m is 0. So what we get here for phi is just this, phi is just g1. So phi has the form of a polynomial. So what we've shown now is that we can express every regular function on A2 without the origin in the same form that we can express it on all of A2, because remember on the affine space A2 we have previously shown that the regular functions are just the polynomial functions, and yeah, this means we are finished. We have shown that we can extend every regular function on the punctured plane to a polynomial function on A2, and this concludes our proof. Thank you for watching. For more algebraic geometry, please refer to my playlist, and see you next time.